So thinking back to our ideas with single value estimates, that is point estimates, we always do have to accept that it's kind of like playing Battleship. You are trying to estimate a point with a point. And either when you do that, you're going to hit
J7.
You have sunk my battleship.
Excellent! Yeah!
or, far more likely, you're going to miss.
B3.
Miss.
And when you miss, you have to bear in mind that you're going to be off by some amount. If, say, you estimate that a mean value is 82 and the actual mean is 80, you will have missed by 2 unitless measurements, where this is our sampling error. It's the difference between what we estimate and the actual parameter that we are trying to get an estimate of. Now, generally, we don't actually know that value, but it is just the representation of how far away we are from the truth, as it were. Although we'll see in Chapter 7 and beyond, the truth of parameters is a bit up for debate. Anyway, the main thing we're going to talk about here is instead that's what I'm looking for, equivalent of that idea in the context of interval estimates, where we have what's called the margin of error instead. Now, what the margin of error represents is the maximum distance we can have between a point on our interval and the actual parameter we're trying to estimate, which happens to occur right in the middle of our interval. So usually when we're trying to remember what the margin of error is, it's better to think of it as just being the radius of the interval. So if you have an interval from, say, 20 to 24, you can see at the middle in there is at 22, and going to either end would take 2. 22 to 24 is 2, 20 to 22 is 2. Where we get this margin of error, we calculate this margin of error in terms of our distribution, in terms of our critical values, and the specific information that we have. Where to get E, we multiply the critical value, that in this case we denote Z sub C because we're talking in terms of normal things, by the standard error to talk about how much variation we have in our data set that we're trying to represent, which we write as sigma sub x bar, or a bit more exactingly, Z sub C times sigma over root n. But to me this is very unrealistic, because if we think back to Chapter 2, when we defined sigma, we explicitly defined sigma in terms of mu. So, looking at those values, it seems somewhere between unlikely and impossible that we would somehow be in a situation where we know the standard deviation for the population and not the mean for the population. Where saying we have the result but not the cause. It'd be like saying you could make a cake that uses flour without having flour. It just doesn't make a whole lot of sense to me. Which is why I generally don't use this construction very much. It makes assumptions that just don't feel like they could happen in reality without some strange circumstance back-ending it in the way that you'd really only see in a homework problem. So that's why I don't generally show you guys much with actually making these intervals for z-scores. But we will see the adjustment we can make on this, where if instead we have a margin of error in mind, we can talk about the minimum sample size required to get it. That is, if we want E to be some value, we can flip this formula around. We can multiply over n, divide out E, and square the whole thing to get that our minimum sample size is Z sub C over sigma divided by E quantity squared. And that's what we'll look at next in our example here for how to run that. But before I get into that example, I do want to be very clear about something, because it's easy to lose focus on where this comes from. But let's remember, we're looking at a standard error, and we're talking about using a sample mean to say something about a population mean. And what that says, in symbolic language, is everything in here gets built off of the central limit theorem. So just bear in mind that even though we're not going to explicitly be calling on it every single time we do one of these problems, everything we do here, at the very least implicitly, depends on the central limit theorem. Otherwise it wouldn't work.